This problem is about shape and hybridization of more complex molecules. Please read the problem, propose a plan to solve the problem, and then let's compare the answers after a few minutes. The plan to solve this problem consists on counting the number of electron groups around each carbon and oxygen atom present in this molecule. This will also help us determine the number of hybridized orbitals and the type of hybridization. We need to keep in mind that a single bond is a single bond, and a double bond consists of a sigma and a pi bond. We also need to keep in mind that trigonal planar shape corresponds to sp2 hybridization. Okay, so let's begin then by redrawing the molecular structure of aspirin. And we are not going to use the shorthand to represent this structure at this time, because this will help us count the different electron groups that we need to count. So once we have confirmed that we have properly represented the structure, we need to make sure we have all the sigma bonds and the pi bonds indicated in the original structure, or sigma bonds and double bonds, I should say. And now we are going to start by assigning a number to each of the carbons. So let's assign this carbon is going to call carbon 1, this is going to be carbon 2, this is going to be carbon 2, this is going to be carbon 3, 4, 5, 6, 7, 8, 9 carbons. And then we are going to do the same thing with the oxygens. I'm going to call this oxygen 1 prime, 2 prime, 3 prime, and 4 prime. I also will take into account that when we consider the Lewis structures, we need to consider the lone pairs of electrons that are present in the atoms in this system, which will correspond in general to oxygen. So I'm going to add 2 lone pair of electrons to each of the oxygens that we have in this particular system. Okay, so now what is going to be key here is to figure out what carbons have an sp2 hybridized orbital or orbitals. And so let's start by looking at number 1. And number 1, based on the number of bonds that we see around, we have 3 sigma bonds. We know that this is going to have it's going to be an sp2. Carbon 2 also has 3 sigma bonds. It's an sp2. Carbon 3, the same. Carbon 4, the same. Carbon 5 is the same. Carbon 6 is the same. Carbon 7 is the same. Carbon 8 is the same. So in general, we know that all these carbons have trigonal planar shape. We have one more carbon that we have not considered, and this is going to be carbon 9. And because the number of bonds that we have present in carbon 9 we know that this is going to have to be an sp3 hybridization system. Okay. We also can do the same analysis of hybridization for oxygen. So for oxygen, for sp2 hybridization, we are going to have oxygen 1' and oxygen 4'. And we also have oxygens with sp3 hybridization, which would be oxygen 2' and oxygen 3'. Lastly, let's count the number of bonds that we have present in this system. So sigma bonds. And I'm going to circle this so that it's easier to figure out which one we are referring to. So for sigma bonds, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 sigma bonds. Total pi bonds, we count where double bonds were present, and each of them contributes to 1 pi bond. 1, 2, 3, 4, 5 pi bonds. And lastly, localized pi bonds. That is, those that do not have a resonance structure. We have only one corresponding to this oxygen, and between oxygen and carbon, and one corresponding to this oxygen and carbon. The other pi bonds are delocalized because this part of the molecule here could potentially be written using different resonance structures.